Okay, for homework 2, parts A and B, we're going to start with Fourier's law in order to show how our heat will be transferring throughout our system. In this case, our system is just going to be a bar in which we have a section here along our x position. We'll call the first part of our section x prime. We'll call the distance of our section dx, and then our next part will be x prime plus dx. So to represent the energy coming into our section from the section to the left, we will use our Fourier's law once again. So that will be our Qx is just equal to negative K, thermal constant, times our area, a change in temperature, and our change in position. And then the energy going out is also Qx minus Ka, but this is going to be at our x position is equal to x prime, and we have K minus Ka again, change in temperature, change in position, at our position x prime plus dx. So that's what's going in and out, but what's currently in our section, our metal, is equal to rho Vc times our change in temperature with respect to time. So this is showing the changing thermal energy within our block that we've determined. So we can represent our volume of our section as the area times our dx, which we've defined. So doing this, we can combine all of these equations to show that our total energy inside of our system, so we'll go rho area times dx times c, change in temperature with respect to time, is equal to what we have coming in, so minus Ka, change in temperature with respect to position. Then, since this is going out, well, it will be negative, so negative, negative again, Ka, change in temperature with respect to position. And now that we have this, we can cancel out our area, which just leaves us with K. This can just scribble that out, make it a plus, which makes it a little easier. And then we can pull out our K, so we will end up with our rho dx times c, change in temperature with respect to time, is equal to our negative K times our dt and another dt, so we can represent this as our second derivative with respect to temperature, not that squared, but squared here, times our temperature, and then that's over dx. But what we can do here is divide across by rho dx and c to give us our change in temperature with respect to time is equal to our negative K over rho C times the second derivative of temperature with our change in position squared. So that is part A, giving us a time-dependent change in temperature. And what we'll do now is turn this into more of an algebraic equation, so we can use Python in order to numerically solve what we're doing. So we know that our change in temperature is going to be equal to our temperature at, so we should define our positions. So our time steps for temperature will be n, so because it's the change, we'll have our temperature n plus 1, so our next temperature minus the temperature it used to be. And what we can do is, since we will end up having so many of these areas, is represent each one with a letter. So we can call this at our temperature J. So our temperature J of n is the block we're in at the current temperature. And we know that the block we're in at the next temperature, n plus 1, which can be represented as our dt. This is over change in time, so minus our k rho c, which can be represented as our thermal diffusivity, or alpha, and then we have our second derivative with respect to temperature and our dx squared. So our dx is just going to be our change in position, so our delta x. So we can simplify this a little bit, making it our second derivative temperature over delta x, and then divided by delta x again would give us what we're looking for in terms of being the same as our dx squared. So another way we can represent our second derivative of temperature is by having our first part. So this will be all at our current temperature, which is our T of n. However, this will be at our next position over, so the position to the right, minus our current temperature at our current position, all over our change in x. And then the second part of this we'll subtract again, this time starting with our current position and current temperature, subtracting our current temperature, however, at the position to the left. This again will be over our change in position. And lastly, this is still all over our change in position. So what we can do now is kind of simplify things out a little bit. We'll pull out both of these changes in position, and we'll need to bring across our dt and simplify, or not simplify, but move things over to isolate how we will calculate our temperature at, or our next temperature at our current position. So the first thing we can do is multiply across by our change in time. So we end up with our tjn plus 1 minus tjn is equal to our thermal diffusivity times our change in time, or our time step, and all of these change in x's can be brought out, so over delta x squared, and then because that's all brought out, we see that we start with our t of n at our position to the right, minus current position, current temperature, minus again current position, current temperature, and because of this minus sign, our tj minus 1 will end up being positive. So this gives us tj plus 1 at our current temperature minus 2 of our temperature currently at our current position, and adding our temperature currently at the position to the left. And then the last thing we need to do is just move over our current temperature. So we'll just add that to both sides. So plus Tj of n. And this is how we will algebraically solve for what the next temperature T n plus 1 at our current position J will be. Okay. For homework 2, part 1, for part C, we're going to be doing Python now using the equation we just derived in order to simulate this heat diffusion within our material. So one thing that's important to know is our thermal diffusivity times our change in time divided by our positional step squared is are going to be calling that R, and later we'll go into detail into why this R is bound to be within a certain range. So we'll go back to Python, and what we have is numpy and our make subplots and our lineage for later. Our R in this case is going to be 0.5, and we're going to split our material into 100 different parts. So we need our array of temperatures, which is going to be equal to our NP full. We want n number of things, and we want them to all be 20 degrees Celsius. We then need to change our first and last values of our array of temperatures in order to be 50 and 80, because we're going to have constant temperatures at each end of our bar in order to have any thermal diffusion happen. So our first temperature will be 50 degrees Celsius, and then our last temperature in our list is going to be equal to 80 degrees Celsius. We need a position in order to plot these, so our position will be NP a range of n, so just a list of numbers from 0 to the end of our list. And then we will do figures to add scad. Our figure is equal to make subplots. So our first thing we'll do is we're going to add a scatter for our initial condition. So this is going to be our x will equal position, our y values are going to be equal to our temperature, and the name for this is going to be just 0. So our first step in time, and then next we need to run this simulation many times. So for I in range do 50,000 for this example, we're going to need to calculate a new value of t, but since our boundaries are constant, we need to define which values we'd actually like to change. So it will be our second value all the way up into our second last, but because of how this is cut off, -1 will be our second last, and then so our next time is going to be equal to our current time again, which will be the same thing, second all the way up until second last, plus our R value times what we have derived. So our next position minus our current position plus our previous position. So to do this, we need to go back to Python, in which we will have our t of our third position all the way until the end, minus what we have currently, however there are 2 of them, 2 times t from our second to our second last, and then again adding our t of our all the way from our beginning up until our third last. So that will calculate our new t, and then we will say if our I value and our remainder when divided by 1,000 is equal to 0, So what this is doing is basically we're running it 50,000 times, and if we have 50,000 lines, it will look very cluttered. So we'll only be adding something to our plot every 1,000 time steps. Our again x position, x will be our position, our y will be our temperature, and the name for each one of these is going to be our string, and then we want this just to be I. So we'll see if this has any issues. One dimensional but two word index. Whoops, I was using a comma instead of a colon. Does that do anything? And then we'll just show our figure. So this has 50 lines, and we have each one. So we can see that our first time step is 0. Just give me this one. So we have our 0. So we have our left all the way at 50. Everything else is at 20, and our temperature on the right is at 80. You can see as we go on, this curve begins to become a straighter line, and as we get closer and closer, we can see that it becomes relatively constant. So now what happens when we change our R to be even just a little bit higher? We can see that these numbers are enormous, and this is no longer stable, and it is exponentially growing. For homework 2, part A, for our last part, we're going to be discussing why that changing our R value above 0.5 causes our system to pretty much expand to infinity based on its stability. So what we're starting with was our differential equation we derived for our changing temperature based on our changing position and temperature with respect to time on the left side, and what we were given was a solution to this differential equation, which is our temperature is equal to the exponential minus alpha k squared t and the exponential of I kx. So if we were to do this equation for a specific temperature and position, this would slightly change things, and we'd have our exponential of minus alpha k squared, our change in time, times our n, which would be whichever time we determine it to be, which step, and then again our exponential of our I kx. However, instead of just kx, be our change in x times our j, our current, previous, next, or j position. So once we have our equation based on a certain position and temperature step, we can alter this a little bit to give us something else. So our current temperature at our position, however, this is going to be the next position. We know in this situation our delta t is going to be equal to 0 since we are still at Tn, which was our current time step for our temperature n. So what that means is this will become 1, meaning our exponential over here will end up looking something like this. So we have e to the I k delta x, and this is going to be multiplied by our previous temperature at our previous position, or the current one, so t j of n. And if we were to do this again for j minus 1, we will get e to the I kx again, I k delta x again, times t j of n. However, the one change this will be for j minus 1 is this here will be negative. So what we can do now is up here, as you can see, we have these tj plus 1s of n with more tj's and our tjn plus 1s. So we'll need to start substituting some of these in for the equation. So let's rewrite this. We have our tjn plus 1 is equal to our tjn plus our r multiplied by our tj plus 1n, which we know is going to be eik delta x times tjn minus 2 tjn and plus our tj minus 1n, which we have here, which is going to be plus e to the minus ik delta x times tjn. So what we can do now is pull out our tj from all in here, which leaves us with our tj of n plus 1 is equal to tj of n plus tj of n times r multiplied by our eik delta x minus 2 plus our eik delta x. One more thing we can do is pull out this tj, so we get our tjn plus 1 is equal to tj of n 1 plus r multiplied by eik delta x minus 2 plus e to the minus ik delta x. Euler's formula reminds us that e to the ix plus e to the minus ix is equal to 2 cosine of x. So using what we know about that, we have our ei to the delta x. So what we end up with is simplifying this again. So our tj n plus 1 is equal to tj of n 1 plus r times 2 cosine, and instead of x we have ik delta x, so what we end up with is cosine of k delta x minus 2. So from this we can pull out the 2, giving us 1 plus 2r times the cosine of k delta x minus 1. And this is important because we know our next step in time for our temperature at our current position is equal to our current position plus, where'd they go? Our current position times our 1 plus 2r cosine minus this. So what we can do here is we know that the absolute value of this is going to always be between, or not between, but be absolute value of our 1 plus 2r cosine k delta x minus 1 is always going to be less than or equal to 1. So what we can do with this is we know that if the absolute value of it is that way, we have our 1 plus 2r times our cosine k delta x minus 1 is less than or equal to 1 or greater than or equal to negative 1. We can now subtract this 1 from both sides, giving us negative 2 is less than or equal to 2r times cosine k delta x minus 1, which is less than or equal to 0. And we know that because the maximum value of our cosine function is 1, we will get 1 minus 1, so the maximum we could ever get to is 0, meaning we don't have to worry about this right side of the equation. So what that leaves us with is minus 2 is less than or equal to 2r times our cosine k delta x minus 1. And from here, we know that our maximum value, or in this case minimum, is going to be negative 1 for our cosine, meaning that the maximum this could be is going to be minus 2, which would be negative 1 minus 1, giving us minus 2, which ends up giving us negative 2 would be less than or equal to 4 times r, or a negative, and we would now just divide across by both sides by 4, giving us r, and flipping the sign. So that gives us r is going to be less than or equal to 2 over 4, which is 1/2. So we know that our r is less than 1/2 based on this analysis, which aligns with what we saw in Python, where if it goes above 1/2, it tends to infinity because our solution for our differential equation no longer holds true. Alright.